Homework 14, Logarithmic Functions, Video 2. Evaluating logarithms, exponent rules. In the previous video, we introduced the concept of a logarithm. It's basically a question. What power turns the base into the argument? And some of them are pretty straightforward, but some of them will require you to be familiar with some exponent rules that we've already seen. So as we go through these examples, I will be reminding you of those exponent rules and actually introducing you to a new one that we haven't seen yet, and show you what those exponent rules look like in the context of logarithm rules. So let's start with this first one. Log base 13 of 1. Remember, a logarithm is simply asking you a question. The question this one is asking you is what power turns the base, which is 13, into 1. So what power would we put on a 13 to get an answer of 1? If you don't know the exponent rule that's in play here, this would be a tricky question to answer. But in the previous series of videos, we had an exponent rule that talked about a power being equal to 1. That exponent rule was anything to the 0 power is equal to 1. Well, except 0. There is the stipulation that the base can't be 0. Oh, by the way, in case you haven't figured it out, the reason it's called the base here is because it's the base here. How convenient. So according to that exponent rule, what power could we put on a 13 to turn it into 1? The answer is a 0 power. So the answer to this logarithm is 0. I want to pause for a second and say that if you're frantically trying to press the buttons on your calculator, one of them says log. To put this in it, any of these, or even the previous ones, there is a way to do that. But the button on your calculator has a specific base assigned to it, and we'll talk about how to overcome that, if not in this series of videos, then in the next series of videos. But for now, all of these can be evaluated using basic arithmetic and exponent properties. So log base 13 of 1 is equal to 0 because 0 is the power that you put on 13 to turn it into 1. Now, can we transform this into a logarithm rule? What made that problem equal 0? Was it the 13? No, it was the 1. So we can write a corresponding logarithm rule that says the log of 1 with any base, or any allowable base, is equal to 0, because anything to the 0 power is equal to 1. Let's take a look at this next example. Log base 7 of 1 over 343. Now, if you watched the previous video, you may recall that 7 to the 3rd power is 343. But we're not trying to get 343. We're trying to get 1 over 343. So the question we're answering here is what power turns 7 into 1 over 343? Or in other words, 7 to what power is equal to 1 over 343? Do you think you know the answer? If you do, great. We'll see if you're right in just a moment. If you don't, then we did an exponent rule that will help us. And in the previous series of videos, we had an exponent rule that said some things turn into fractions. And that rule was any base, except 0, to a negative power, we'll say the negative n power, is equal to 1 over x to the positive power. So I know we're looking for a negative power, but which power is it? Well, if we capitalize on the knowledge that 343 is 7 to the 3rd power, then we can rewrite this problem as 7 to some missing power is equal to 1 over 7 to the 3rd power. And now, according to this exponent rule, that power is negative 3. So log base 7 of 1 over 343 is negative 3 because 7 to the negative 3 power by this exponent rule is 1 over 7 to the 3rd power, which is equal to 1 over 343. So can we turn this into a logarithm rule? Sort of. So let's capture the structure of what made this work. We had some random base, and for our argument, we had a fraction that had 1 on the top. But what did we have on the bottom? We had a power of the base. So the base raised to some power n. And so what exponent would you put on this base to get this expression? Not n, but negative n. So anytime we do a specific problem whose answer or flow depends upon the structure of the problem, we can turn that into a rule by removing the specific values and replacing them with generic values, aka variables. So when you see a log of a base of the reciprocal of a number, you should probably expect a negative answer because negative powers reciprocate. Now this last one, we haven't talked about yet. So I would not be surprised if you're looking at this one and thinking, I'm not sure what to do with it. First off, that's not a square root of 25. It's a cube root. We don't deal with cube roots too terribly much, but I want to quickly review what it means to be a cube root. So we'll come back to this problem in a second. But for example, if we have the cube root of 8, you may or may not know that the answer is 2. But do you know why it's 2? Because 2 to the third power is 8. When you square root a number, you get the value that when you square it, you get back what you started with. Like the square root of 49 is 7, because 7 squared is 49. But when you cube root a number, whatever your answer is gets raised to the third power, or cubed if you will, to give you back what you started with. So the cube root of 8 is 2 because 2 to the third power is 8. So it's important to understand what that even means. And 25 does not have a nice clean cube root. You might think it's 5, but it's not. Because if you did 5 to the third power, you would get 125. The square root of 25 is 5, but the cube root of 25 is irrational because 2 cubed is 8, so 2 is too small of an answer. 3 cubed is 27, so 3 is too big of an answer. The answer to the cube root of 25 is somewhere between 2 and 3. But again, it's an irrational number. It's a decimal that goes forever and never repeats. So how do we attack this one? Well, we have to use an exponent rule that, with the right amount of time, I could get you to tell me, but we don't have that time. So I'll just tell you what it is. The exponent rule is, if you raise anything, we'll call it x. And really, what I should have been doing instead of using x is use b for base. I mean, they're all saying the same thing, but then it establishes some consistency between the exponent rules and the corresponding logarithm rules. So I'm going to start using b for the generic base. But the exponent rule being in play here is if you have any base raised to a fraction power, we'll call it m over n. Doesn't really matter what 2 letters we use. A fraction power tells you to do 2 things to the base. Number 1 is to put a power on it, and that's the numerator. But the denominator tells you the type of root to take. So if it was a 2, it would be a square root. If it's a 3, it's a cube root. If it's a 5, it's a fifth root. But this is an exponent rule that we don't run across too terribly often, but we need it now. And for those of you heading towards calculus, you will need to know this rule as easy as you know that 1 plus 1 is 2. So let me do a real quick example of this before we go back here. For example, let's say I ask you what 343 to the 2/3 power is. Well, when you raise something to a fraction power, the top really is a power, but the denominator is an index. So we're taking the cube root of 343 squared. And one thing worth mentioning is the top number is a power, the bottom number is an index. That's what you call this little number, but it doesn't matter which one happens first. So you could do the cube root of 343 squared, or you could do the cube root of 343 squared. Either one of those would be correct. Do you know the cube root of 343? Do you know what number you multiply 3 times in a row to get 343? Hopefully by now you know it's 7. And then 7 squared is 49. So when you see a fraction power, that's how you would approach it to evaluate it. but we're not trying to evaluate any fraction power here. We're just looking for a power. So, how can I do this logarithm problem? Well, a logarithm is asking what power turns the base into the argument. So we're being asked what power, we use a square for it, would you put on the base, 5, to get the cube root of 25. Now the problem that I'm running into is that I'm looking for the base inside of here and I don't currently see it, but I know that 25 is 5 squared, and you probably do too. There's no probably, you know that 25 is 5 squared. What's not obvious is that you need to change it to 5 squared here in order to make these bases match so we can take advantage of this rule. This rule says if you have a power inside of a radical, then you can write a fraction power by putting this number on top of that one, by putting 2 on top of 3. So the answer to what power turns 5 into the cube root of 25 is 2/3, which means that the answer to this logarithm is 2/3. That one's a little tricky because not only do you have to use an unfamiliar exponent rule, you have to be willing to manipulate some of the numbers in the problem to expose the base. But by rewriting the 25 as 5 squared, it exposes the base of 5. It gives us a structure that resembles this, and this rule says that we can rewrite it as the base raised to this fraction power. So the base raised to this fraction power. And I did write it correctly, I just did my fingers incorrectly. Do it like this. All right, so that one's a little tricky, but welcome to the end of college algebra.